So we start recording. All right, guys. So where should we start?
Number one, four maybe, please. And I have one question, Professor.
Yeah. Yeah.
For rank question, we just have to do the rational form and whatever leading one, we just have to tell, right? Or do I need to show like all the rational form there? I mean, reduce to the echelon form
Reduced row echelon form, right? So the reduced row echelon form
or
is
nullity,
yeah. The reduced row echelon form gives you all that information.
right? So like, do you need to show like all the work, or you just like plug in and just?
Show me all the work, man.
No, I mean, like, because you remember you say like for this exam we don't need to do the like whole thing. We can just plug in our calculator, right?
Okay, yeah. So at this point, I'm not asking you to show the row reduced echelon form by row reduction, by Gauss-Jordan elimination. I'm not doing that no more.
Okay.
Yeah.
Okay. Thank
I, the point was exam one, we took care of that. Now exam two, I believe you know how to do it at this point,
you. Right.
and yeah, there's no merit at this point to show me if you can do that. It's like, all right, we get it. So put it in your calculator, row reduced echelon form, and you should be able to interpret what that row reduced echelon form is.
Okay.
Okay. So which one did you say?
I'm just saying like maybe we can start from like 1 4,
This
number
one?
1 4, yeah.
Okay. So this is a perfect way to start because your quiz on Monday will
Right.
cover something like this.
Yeah.
So I'm literally, I told you with the bullet points, I'm gonna tell you this now audibly.
Okay.
You're gonna be given a transformation, a linear transformation, and you're gonna have to show me that it is linear. That's the first thing. The second thing is you have to be able to find the standard matrix representation of that transformation. That's two, the second bullet point. Third bullet point that I gave you is that you have to find the bases, be able to find the bases for reduced row echelon, for the row space, column space, and the null space. Then you have to learn how to be able to tell me the rank of the matrix, the nullity of the matrix. So that's gonna be that's gonna be your quiz, and this is a perfect way to start. So we're given the transformation here, but we don't know if it's linear or not. We have to check. So look at number four. So then how do we check? So let me add a, so let me ask you guys, how do you check?
We have to check for addition and for multiplication and for I think these two is good enough.
So let's be very clear. So the transformation T is linear if, what? If T of U plus V, right, equals T of U plus T of V. This is one of the first properties. If for all, I should say, for all, and for all U, V in R N. And let me just include that information here. We have a transformation that takes things in Rn and maps it to things in Rm, right? That's the notation we use. So then if you take anything in Rn and you add these things together, when you apply the transformation to that sum, it's equal to finding the images, right? Remember that's what this means. So the image, just in general, the image of V under T is given by this notation, T of V. So you see how now we're kind of generalizing these ideas that you've talked about before. Uh, you guys are used to functions and then you have input output, right? But now we're talking about not just any old output. Um, Normally the connotation is that when you have an output, you have a number. When you have a function, you're plugging in a number to another number. But now we have extended that idea of functions to include other inputs like vectors, for example. So we're given a vector, and under a transformation, you output a new vector. So that's what T of V represents. So the image of the sum of U and V is equal to the image of U plus the image of V. Okay, so that's the first property. The second property that must hold is that when you take T of CV, where C is a scalar, it's equal to C times T of V. This is for all V in Rn and any C in R. So C is a scalar again. Okay, so I want to check these two things. So if we go back to our transformation, this is our transformation. I'm gonna write it this way though. I'm gonna write it as a column vector, xy, right? Here they have it as a row vector, but I'm gonna rewrite it as a column vector. So T of xy equals 2x, what is it? 2x plus y, and then x minus y. Okay, so I want to check for linearity. So what's the first thing I have to do? I have to check that first property. So how do we check that first property? What's the first step?
We do the addition like separately, like two
Well, what
there. So like so we just like x1 y1 and we added with another x2 y2
okay, that's a good
and
idea.
it's
That's right. So we say let u. Well, in this case, where is t coming from? Let's always specify where t. What's the domain of t? Remember what t does, right? Remember what this means. The domain. This is the domain, and this is the codomain. So what's the domain?
XY.
xy
No, the domain is R2.
r2, I mean like from r2 to
Right. This
r2,
goes
yeah.
from R2 to R2. So that means that U and V are going to be coming from what? R2. So we let this be the case. So then U will have the notation, like you say, x1, y1. And then V will have x2, y2. Right? And what we can do is add them. So U plus V will be what? X1 plus x2, y1 plus y2. Right? So we know what U is, we know what V is, we know what U plus V is. And what we're going to do is plug in U plus V into T, which is T of x1 plus x2, y1 plus y2. Now, according to this rule, what's the rule that I have? The rule is defined in this very equation here. First component, second component. When I plug this in, gives me what? The first component of my image, this is my image of xy. The first component is double the first component of my pre-image plus the second component of my pre-image. That's my first component. Then my second component of my vector is the sum of the first component of my preimage with the subtracted by, sorry, it's the difference between my first component of my preimage and the second component of my preimage. So what does that look like for us? It looks like this. At this point, guys, it's just like algebraic step manipulation, really. So it's 2 times x1 plus x2 plus y1 plus y2. And then you have x1 plus x2 minus y1 plus y2. Does that make sense? Any problems with this step? Is it understood?
Yes.
Okay. So then at this point, all I've done was apply the rule to this, right? All I've done is apply this rule to this guy. And I did it. But I want to show whether or not it equals the sum of these guys individually. So then what we do is I can distribute the 2 and I get 2x1 plus 2x2 plus y1 plus y2. X1 plus x2 minus y1 minus y2. Now, do you see where I'm going to go with this? What's next? What can I go from here? Where can I go from here?
To separate?
Yeah, I want to separate that. How do I separate it though?
By 2x plus y. So 2x1 plus y1
Right. So
and
you
2x2 plus
you
y2.
realize, wait a minute, I can rearrange the order of this, right? And I do so because I already know or have a feeling that I'm able to separate this in a way that I precisely will demonstrate the first property, right? Already you can see that, or you should be able to see that. So I'm here, and then I'm just going to separate the sum. So this is 2x1 plus y1, x1 minus y1, right? This is the sum of that with 2x2 plus y2, x2 minus y2. And then what do you say after that? Well, what is this? And what is this?
Linear combination.
If not the image of what? This is the image of u, and this is the image of v. So I just showed in this algebraic long-winded process that t of u plus v is indeed t of u plus t of v. Did my screen is my screen frozen to you guys?
No, it's not.
You can see it? You see me zoom in and out?
Uh, yeah.
You can see me zoom in and out?
Yeah, I believe so.
Like I'm zooming in and out at this moment.
Oh,
No,
no.
you just
Oh, you just see like a red, right? Just yeah. I'm not sure why it's lagging. These are the technical difficulties of Zoom. So this is what I have now. Yeah. Here we go. So do you guys see how I proved or showed the first property of linearity for t? So it preserves addition. The transformation preserves the operation of addition. That's what this statement here means, which is very nice. It's a very nice property to have. So any questions about this?
So if in case it was not linear, like I think the question 2 is not like transformation of u plus v.
Number 2, you say? This one?
Yeah.
Yeah.
So
So this is the scenario where
it
it
is
won't be
not.
linear,
Yeah.
and you can show that. You would
So
be able to show algebraically, oh wait, the linear property, one of them or both of them fail.
right. So if it is one of them fail, like this
One of
the
them
way we
fails,
just
it's no longer
understood,
linear.
need to show more, right?
Yeah, it's no
Um,
longer linear.
and because like I was doing in math tutor yesterday, so
Yeah,
so it was just they were if I follow the same instruction that you did,
yeah.
it will show that it is not. But they were saying, okay, if you want to, there is another way to show that it is not linear for addition. So do I need to show like both ways, or it just if it doesn't work, we just say, okay, this is not linear.
So what's the other way?
Like it's the same, like this one has
Two
uh,
properties.
two side, right? So from one side, like you took this part, right?
Mm-hmm.
And right away show that it is not linear, because like if we take like x1 square plus 2x x2 and like we separate them and
Yeah,
we get like at the end there is another vector left.
yeah,
So if I show up to that part, that's good enough, right?
that's good enough.
Okay,
Yeah.
thanks.
Again, you just have to show that one property fails, and that's it. Hey, Oren, welcome. Yeah. So if a transformation is not linear, one of them will fail, and that's enough. If it is linear, you have to show both properties. But I also mentioned uh, in one of the lectures that you can actually sum up these two properties in one, and it's this property, C of let's see, U plus V is equal to C times T of U plus T of V. If you study this, this this summarizes these two properties into one. You see how this here, if I can separate by a sum, and then so it kind of goes like this. So if T of CU plus V, if it's linear, then I can do this. And then if it's linear again, if it's fully linear, then I can do this. So this property here, this equation summarizes these two properties. So if you can prove that show that a transformation obeys this equation, you essentially kill two birds with one stone, as they say. So you can also do that way. Okay. But I like going through this way just to see both properties clearly. One is for the addition of two vectors, and the other one is for scalar multiplication of a vector. Okay, so let's look at the second property. So the second property, T of C of V, right? And here V can just be XY. So V, I'm just going to write it as XY, which means that CV is CX CY. So this is T of CX CY. And then use the property again. And the rule for the transformation, it's 2x plus y, x minus y. So it's going to be 2cx plus cy, and then it's cx minus cy, right? That's exactly what the rule is. But then you should see very quickly, now wait a minute, I can factor out the c, and then I can factor out the c even more. But this is precisely T of V.
Mhm.
So I just showed again, algebraically,
Solo hay 7 niños.
that T of CV is C times T of V, right?
Pero no, no sé.
Hello, Saul.
Doble spot. El martes doble spot.
So I'm gonna put you on mute, Saul, okay? All right. Does that make sense?
Yes.
So then what do we say? What do we say? Thus, T is a linear transformation. Why? Because it satisfies those two properties. And so then just to piggyback off of this, right? I'm just letting you know what you'll see on the quiz is find the standard matrix representation of T. Remember, every matrix representation can be, every linear transformation can be represented by a matrix, and every matrix transformation can be represented by a linear transformation. They're synonymous. We proved that. We showed that. And that's one of the proofs that you should know how to do. So what would be the, how would we find it? Or how does one find the standard matrix representation?
I think it's 2, 1, and 1, -1.
Good. Right? So now when you do that, once you do this, then you can write it, you can write this. Look, you can write this as A, T of A, where A is my matrix, right? My matrix is A. A is 2, 1, -1, -1. And there you have it. Any questions, any ideas, comments, concerns? Is this clear? Do we know the process of showing linearity of transformations? Do we know how to find standard matrix representations of transformations? Fundamental ideas, very important ideas to have clear and well understood. Anything at all? Yeah, that's usually how it goes, right? Like we've touched upon many things throughout these weeks, and now we are putting more of a fundamental theoretical framework around everything we've done. At first, you see how we started this whole class. We first started with vectors and then just switched right into solving linear systems of equations. And now we're so far deep into this that we kind of forgot what we even like started with. We started with solving linear systems of equations, and now we're talking about linear transformations, which have everything to do with linear systems of equations. But now there's much more to it. There's much more to the row reduced echelon form, the reduced row echelon form. There's much more you could talk about now. You could talk about the rank of a matrix. We could talk about the nullity of a matrix. We could talk about the bases for column space, for the row space, for the null space. So there's so much now, so much more information we can get from the basic things that we learned in the beginning. And now a matrix is no longer just a matrix full of numbers, an array full of numbers. Now this array full of numbers exactly represents a linear transformation. And so that's how you connect numbers to functions to mappings between different spaces. And then all of a sudden, a world just opens up. A new world opens up that you didn't know it was there the whole time. All right, so anything else on this question? If not, where else should we go? Where else do you want to go?
1.2, number 3, please.
1.2, number 3. Which part? A, B, and C? Or just which one would you like to do? All three or one or what?
Them will be fine.
Yeah. The thing is that once you do one, you could do them all. Okay, so 1.3.
1.2.
Oh, sorry, 1.2. So we have V, right? V is what? 3, -4. So where is V? V is what? 1, 2, 3. And it's 1, 2, 3, -4. So V is here. And what do I want to do? I want to rotate this through different angles. I have different angles that I want to rotate it through. So let's look at A. I want to rotate through the angle of theta being 30 degrees. So I want to rotate this guy. So rotate by 30 degrees. And the assumption is it's counterclockwise about the origin. And this is just a shorthand notation for counterclockwise direction. That's why we're moving in this direction, right? And I want to move 30 degrees. I want to rotate this vector 30 degrees this way. I want to know what's the result. What's the resulting vector? Now, if you guys remember, there's a rotation matrix. So what's that rotation matrix? Cosine theta, sine theta, negative sine theta, cosine theta. And we showed that, we proved that to you guys. So the rotation, which is the rotation by angle theta about the origin. I'm going to use r theta comma 0. So theta is the angle of rotation and 0 is the origin. This is a linear transformation. Why is that a linear transformation? Because we showed that this can be represented by the multiplication of a matrix. And we proved that a matrix transformation is a linear transformation and vice versa. So when you learn about this in geometry, they don't tell you the word linear transformation. They just say it's a rigid motion, right? They do say that they use the word of transformations, but it's mostly referred to as a rigid motion. But of course, they don't even talk about matrices because there's no way to include that in teaching it. But for us, the rotation is a left multiplication of a matrix. In this case, a 2 by 2 matrix. So if I want to rotate any vector under this transformation, it's the same thing as taking cosine theta, sine theta, negative sine theta, cosine theta, and multiplying it by xy. That's the whole point of this matrix. When I left multiply it by this matrix, I get the result rotation, which is very useful, very needed. So now if I want to do A, right? A is 30 degrees, so this is 30 degrees. And my particular vector is 3, 4. So then I know my matrix, exactly what it is. These degrees should be known to you all. Cosine of 30 degrees is rad 3 over 2. Sine of 30 is a half. This is negative a half. And this is rad 3 over 2. And you're multiplying that by 3, negative 4. So this matrix multiplication, which you just learned right in the beginning, probably like what, week 3 or week 4? This we used to do all of this just by looking at how to operate, right? How the operation works. But now this matrix multiplication is much more than just giving me a vector. It's giving me the rotation of this vector by 30 degrees in a counterclockwise direction about the origin. So there's a lot more to say with that now. And then if you do the computation, you get something like this. And you could put that in your calculator to get a decimal. Does that make sense? Yes or no?
Yes.
Good. Good. Thank you. So it's good. You know, feedback is good for me. So I can't see your faces. So it tells me how it's going. So I get these numbers. You guys see that? Oh no, sorry. Yeah, you guys see it. So then my result will be what? Like this is like 4, 5, right? And then you get negative 1.6. So it's gonna be somewhere here. Of course, this is not perfect. But this would be the rotation of 30 degrees of V. So this here would be 30. You guys follow? And then if you want to do B and C, it's the same process. What's gonna change are the thetas. If the thetas change, then these numbers change. But the process of finding the result is just left multiplication by that matrix. So it's just more computation. That's what I meant. That if you do one of them, you can do them all. It just changes slightly by computation. Make sense?
Yes.
Yes.
Okay, good. So where should we go now? What's next?
Maybe 1.3, the second one, or number 6, either is good.
1.3, the second
Yeah,
one, this one?
yeah, I just want to like get clear like what is exactly asking.
1.32, right?
Right, yeah, please.
Okay. So what is 2 here? Here is the same old, same old. Same old stuff.
Just the standard matrix, that's it, right?
That's it.
Oh, okay, okay.
This is it. We can do it real quick. Don't worry. We can do it.
I just wanted to like be clear. Okay, this is what I meant.
This is X, Y, Z, W. And what does this give me? This gives me a vector in 3-dimensional space, right? Which looks like X plus W, Y plus W, Z plus W. So good. Now I want to transform this. I don't want to use the word transform. I want to represent T as a matrix and a standard matrix at that. So how do I do it?
Just to represent like 1 and 1 and like 1 and 1 and that.
So
Just
like
this.
the simple ones, right? Like the one we did here with
Right.
4, right? You can see it
Right.
very easily.
Yeah,
Now
1.
this is more complex. Like this has a few more components. Also, should be simple to do. But in order not to to avoid mistakes, you should know that A can be represented as T of E1. The first column of the matrix is the image of the first standard basis vector. Then the second column is the image of the second basis vector, so on and so forth. And since we know we're in R4 for the domain, we have the 4 standard basis vectors. Right? And if you remember, what's the relationship between this symbols here and A? A represents T. T takes vectors in R4 and outputs them in R3. T is represented by a matrix. And a matrix multiplication by the left multiplication of the matrix A. So A must have a dimension of what?
3 by 4.
Pardon me?
3 by 4.
3 by 4. That's right. It must have 4 columns, so it makes sense when you left multiply it by V, right? V will have 4 components because it comes from here. So V has 4 components, and then you have 4 columns. And when you left multiply a 3 by 4 matrix by a 4 by 1 matrix, you get a 3 by 1 matrix, which is a vector with 3 components. So that's why this has to be the case. Okay, so let's go through it. So what's T of E1? Well, that's T of 1, 0, 0, 0. And if you put it into the formula, the equation here, you get what? You get 1, 0, 0. So that's my first column. What's my second column? What's T of 1, 0, sorry. It's 0, 1, 0, 0. Which will give me what? 0, 1, 0. So far, so good. T of E3. That's T of 0, 0, 1, 0, which is 0, 0, 1. And then last but not least, T of E4. This is T of 0, 0, 0, 1, which according to this will give me what? You tell me. What would it give me?
1, 1, 1.
Good. So then what's the matrix representation? What is A then? So the first column will be what? 1, 0, 0. Why? Because this is precisely what this equals. Then second column will be 0, 1, 0. Then the third column will be 0, 0, 1. And then the last column will be 1, 1, 1. And so this is my standard matrix representation of the specific t value, the t transformation that I'm given.
Sorry, Professor. How do you get the E for the 1111?
Okay, so E4 is 0, 0, 0, 1, correct? That's
Right.
what E4 is, right? So I'm applying the transformation t on E4. Now, how does that work? Well, what is t of any vector? T takes a vector in R4 and transforms it into a vector in R3. Now, how are these connected? Well, the first component is x plus w. The second component is y plus w. The third component is z plus w. So that's exactly what I'm going to be doing. But now I have specific numbers. So the first component is x plus w, which is 1. The second component is y plus w, which is 1. And then the last component is 0 plus w, which is just 1 again.
Okay, great.
But this is very systematic. There's nothing, like, it's just, do you understand the rule and can you apply the rule? And if you can, then you can get the standard matrix representation, no problem. No issue. Good. Everybody follow this? So this is 1.32.
Mm-hmm.
Okay. And then which one did you say after that?
Maybe number 6.
It's a great one to do. This is a great one to do. If you can do number 6, then you really understand linear transformations pretty well. Number 6 is not an easy one, and it's the one that's worthwhile doing. So let me what? Hold on. So this is great. It says find the standard matrix A. So this is gonna be good, guys. I want to find the standard matrix A. What do I know? I'm given vectors. They're not the standard vectors. But let's look at them for now, okay? So I know I have 1, 0, 2. I know I have the vector 1, 1, 1. And I know I have the vector -3, -1, 2. Now, what should I check about these three vectors? They all come from R3, right? T takes things in R3, gives you back something in R3. What should I check regarding these three vectors? I'm gonna treat it as a set of vectors. What should I check about this set of vectors? What's the important property to check here? Anyone? No? Nobody? If you have three vectors in R3, what's something we can talk about or try to figure out about the three vectors in R3, whether they are what?
They span or
Right, okay. So can we say whether or not they span? Well, let me ask you this. In R3, what's the dimension of R3?
3.
3. So what does that mean? If the dimension is 3, it means that any basis should have how many vectors?
3.
3. I have 3 vectors. So
Mhm.
I want to know, is it a basis? Well, to show that it's a basis, it must be linearly independent
Independent.
and span.
and span.
But the good thing is I already have 3. I already have 3 vectors in a space that has a dimension of 3. So if I have 3 vectors and the dimension of the space is 3, I only have to check one of the things, whether it's linearly independent or span, because automatically, if, for example, I have 3 vectors in a dimension of 3, then if they're linearly independent, automatically it's a basis and will span, and vice versa. So what I would say is, if I have 3 vectors in a dimension, in a vector space, R3, that has a dimension of 3, I just have to check whether these 3 vectors are linearly independent. If I am able to show that, then it's a basis. And once it's a basis, then I can continue. If I don't know if it's a basis, then I can't go anywhere. I'm kind of stuck. So is this a basis? I should specify for what? Is a basis for R3? Let's check. Let's check for linear independence. This is a little faster to check. Why is it faster? Well, you have a calculator. In your calculator, what I would do is I would put 1, 0, 2, 1, 1, 1, -3, -1, 2. I would make that a matrix. And then what would I do with it to check linear independence?
You will reduce that.
Row reduce it. And if it's linearly independent, then one must be true about the reduced row echelon form. You should get what?
No free variable.
You should get
Sorry, I mean like all leading one.
all leading ones. Very good. No free variables. That's very good. See, very good. Very good. No free variables, which means there must be a leading one everywhere, and there is. You can check for yourself. I get the identity. So it is linearly independent. So if you have 3 vectors in a vector space of dimension 3 that are linearly independent, it's automatically a basis. So this checks out. So it is a basis. For R3. Great. Great. So this is just a pre-step. Now, what do I want to find? The standard matrix again, right? But this is a lot more involved than the previous ones that you do here, right? Like 1, 2, 3, and 4 are the same kind of thing to find the standard matrix, same kind of thing. But 5 and 6 are its own little like their own kind of problem regarding, pardon me, standard matrix. So what will never lead you astray, what will always be helpful is to know that the matrix, the standard matrix representation is always found by plugging in E1, E2, E3. This is just the definition. This is purely definition. So I know that the standard matrix representation will be figuring out what does E1, where does E1, where is it mapped to under this transformation? Where is E2? What's the image of E2? And what's the image of E3 under the transformation of T? The problem at the moment is that I don't have the image of E1, nor E2, nor E3. I have the images of other basis vectors. As we just showed, right? This is a basis because they're linearly independent in a dimension of 3, in a three-dimensional space. So these themselves are bases, but I want to know the relationship with these bases. We're going to get into this much more. Most likely after spring break. But this is a crucial part of linear algebra, is changing from one basis to another. Now, why is it so useful to have bases? Well, one thing about bases, not only are they linearly independent, but they also do what again?
Span.
They span. Now, what does that mean? What does that mean? They span the space. What does that mean?
Yeah, we can multiply and make it bigger or smaller.
Well, span is the set of all linear combinations. And we also proved that a basis, and I think you proved this on quiz number 3. A basis represents any vector uniquely as a linear combination. Right? Isn't that what you guys showed? So what we're gonna do, guys, is say, well, let's call these vectors something. Let's call this like V. Let's call this U. Let's call this W. Is that okay? So we just call them vectors. I know T of V, I know T of W, and I know T of U. Now what I'm gonna do is this. I'm gonna say, wait, what transformation A1 V plus A2 U plus A3 W, what linear combination gives me E1? So I want to find what A1, A2, A3 is. So I'm gonna do this. I'm gonna do a matrix VUW, right? So VUW is precisely what I have here. This is V, this is U, this is W. This is gonna be 1, 0, 2, 1, 1, 1, -3, -1, 2. These will be my unknown coefficients. And this will be 1, 0, 0. So this is gonna be just one system to solve. So I'm gonna solve. Then I'm gonna have the other one. This is gonna be B1 V plus B2 U plus B3 W equals E2. Gives me the same kind of matrix, 1, 0, 2, 1, 1, 1, -3, -1, 2. B1, B2, B3. This gives me equal to 0, 1, 0. Are you guys following this? Then 3, C1, V plus C2, U plus C3, W. This equals E3. In other words, 1, 0, 2, 1, 1, 1, -3, -1, 2, C1, C2, C3, 0, 0, 1. You guys see what I am doing so far? So I check for a basis. I know the images of a basis. I'm going to rewrite the standard basis vectors in terms of the other bases. To do that, I have to solve 3 systems of equations. And I can solve them because these vectors are all linearly independent. So it's invertible, an invertible matrix. Here we go. So I need to know the inverse of this matrix to figure out the solution. So I can do that. A1, A2, A3. I can figure out those things. I can figure out B1, B2, B3. And I'll be able to figure out C1, C2, C3. Can anybody help me with this? Well, I should ask, does anybody have any questions about what we're doing?
You said we have to get the inverse of each combination, if
Well,
I'm not mistaken.
I have 3 systems of equations, right? And I have
Yeah.
I have 3 matrix equations, but they're using the same matrix. This is the same matrix, same one, same one, same one, right? This looks like this right now. A, X, B. How do you get X? Well, don't you have to do A inverse B? Right? Like that's how we solve these systems, given that they're invertible, and it is. This is invertible matrix. The row reduced echelon form is identity. The determinant is non-zero. So the inverse exists. I can find the inverse matrix. But you can just put this in your calculator to figure that out. So let me help you guys out. So with your matrix, with your calculator, you can go to second matrix. I'm going to edit the matrix 3 by 3. And the matrix I have is 1, 1, 0, sorry, -3. Whoops. Looks like I can't. Hold on. Okay, so 1, 1, 1, -3. Then you have 0, 1, -1. Then you have 2, 1, 2. Good. And then I can edit another matrix. In this case, I'm gonna do a 3 by 1 column vector. And this will be 1. Okay. Now what I can do is I can go a second matrix again. Pick A, so I have that matrix, and just literally put raise it to the -1 power. That's how easy it is on a calculator to find the inverse. Then I multiply it by the column vector B. Press enter, and I get some kind of fraction. So let me convert that to a fraction. So I get these coefficients. So my coefficients are 3, 7, -2, 7, -2, 7. Does that make sense? And I'll just go ahead and do 3 by 1 again. In this case, this one will be the one that has the vector 1 here, right? And then I'm going to do that again for D, and D will be the column vector where it has the 1 on the bottom here. So then I can do this thing again, but instead of B, I'll be using C. Press enter. So I solved the other one. So let me just make that into fraction, because most of these are fractions. So I get -5, 7, 8, 7, 1/7. And then last but not least, I'll have this, but then second matrix, I have D. Another. I have 2/7, 1/7, and 1/7. Any questions about what I've done, how to do it on a calculator? We know how to input matrices. Now we know how to find inverses. Just raise it to the -1 power. That's as simple as it gets on the calculator. And you can multiply matrices with vectors, matrices with the correct size matrices, and you get vectors, you get matrices back. So everybody clear with that?
Yes.
Okay, so I'm gonna go back to my iPad screen. So look what has been done so far. Got a basis. Great. I want to find a standard matrix representation of T, which requires me to know E1, E2, and E3 and their images. I don't have that at the moment. What I do have are the images of the other basis. So guess what I should do? I should rewrite E1 in terms of the basis vectors. I should rewrite E2 in terms of the other basis. And I should write E3 in terms of that basis as well. Now you may say to me, but why is that necessary? Well, the reason why is because I want to find, don't never forget the overall goal. My overall goal is to figure out this. To figure out the standard matrix representation, I must figure out this. So I want to figure out, what is T of E1? What is that? Where is that? What is that? I don't know at the moment, right? But what do I know? I do know, now I figured out that the correct coefficients to represent E1 as a linear combination of V, U, and W are these coefficients. So I can write it as the following. I know that 3/7 of V plus, minus 2/7 of U minus 2/7 of W. That's precisely E1. And my screen froze again. My apologies. Don't know why. This is lagging or stopping in the middle of. Okay, it took way too long. Do you guys see something or no?
No.
No, right?
So
Yeah. Let me just try one more time. You guys see it now?
yes,
Mm-hmm.
Okay, so you guys with me so far? So I represented E1 as a linear combination of V, U, and W. I found the precise coefficients for each V, U, and W that would give me E1. Now, you may say, but why is that good? Well, T is linear. Maybe now you'll see why it's so useful, why linearity is so useful. Well, if T is linear, then I can do this. And I can do this. And I can do this. You guys see that? Why can I do this? Because T is linear. That's why it's nothing to scoff at when you have a linear transformation. It makes computation very easy. And why is this good? Well, don't I know what T of V is? I do. Don't I know T of U? I do. Don't I know T of W? I do. So that's why it's so important. That's why bases are so important. Once you identify where the bases vectors go under the transformation, you know where everything goes. That is the big idea. If you know where the standard basis vectors are mapped to, then any other vector in the original space that you're in the domain space, any vector you choose, I know where that vector will be because I know the standard basis vectors where there will be. That's a very powerful thing. So now I know this is what? 3/7, and then you multiply that with 2 negative 3/10 minus 2/7. What is it? 138 minus 2/7 -5 -11 and 7. And using your calculator, I would suggest might be a little easier to deal with, but let's see if this works out for us. I'm gonna factor out the 1/7 for now. I'm just gonna multiply by 3. What do we get? We get 6 negative 930. Multiply this by -2, and I'm gonna have -2, -6, -16. And then I'm gonna also add by positive 10. And then 22. And then I'm gonna have -14. At this point, guys, it's just computation. It's not nothing like out of this world. I get a 14 as a result when I add the first component. And then what do I get here? Don't I get a negative 15? Don't I get 7? And then for the last one, don't I get 0? So when you take a seventh of that, don't I get 2, 1, 0? You guys follow?
Mm-hmm.
Did you guys see? Like, I know that's what I said. This is a great problem to do because you get everything all at once. You get basis, you get linearity, you get span, you get linear independence. You understand the fundamental reason why bases are useful in knowing where the images are, so you know where everything else goes. So because I know where V, U, and W go under T, then I know where E1 goes. E1 goes to what? To 1, 0. Which is precisely what? It's precisely going to be that first column. Now I need to know. So this is the first column of A. You see why this is useful? Now what's T of V2? Same idea, right? But now I'm using a different coefficient. I'm using negative 5, 7. And it's what, V? Plus 8 sevenths. U. And then plus what? 1/7 of W. Which is the same thing as saying negative 5/7 of T of V plus 8/7 of T of U plus 1/7 of T of W. And again, I know what this is. This is negative 5/7 of 2, negative 3, 10 plus 8/7 of 1, 3, 8 and 1/7 of negative 5, negative 11, 7. I think this is going to work out for me as well, the 1/7 part. So this becomes negative 5, 2, negative 3, 10 plus 8, 1, 3, 8 plus negative 5, negative 11, 7. It just becomes computation at this point. You get 1/7. And what is this? Negative 10, 15, negative 50 plus 8, 24, 64 plus negative 5, negative 11, 7. What do we get on the top? Don't we get negative 10 plus 8 is negative 2? We get negative 7. What's the second component going to be? You get 39. You get 28, right? And then you get 14, 21. These numbers work out very nicely, okay? This negative 1 doesn't always happen. You get 4, you get 3. What is this? Second column. Okay. Agreed? Am I going too fast? Am I going too slow?
Really quick, I kind of missed it. For E2, the scalar multiples, how did you get the negative 5/7 and 8/7 and 1/7? Oh, okay. I got you.
That's right. This is where you have to make sure, like you're like Spider-Man in a way, right? Like you got the web here, and like the web here. So don't forget that these aren't like isolated things you're solving. You're solving so that you can do this. It's not just in a vacuum. You're not doing this just isolated. They're not isolated solving systems that are being solved. They're all being solved so that you can precisely know what E2 is going. So now I know my second column of A. My second column is what? Negative 1, 4, 3. And I just have to do this one more time, and I get where E3 goes. And then I have the standard matrix representation of T. And once I have that, then I know where everything else goes. Okay, so let's do this one more time. So T of E3. It's T of, and then I go to the third system that we solved. We got 2/7, 1/7, 1/7. So you got 2/7 of U plus 1/7 of V plus 1/7 of W. Did I switch this around? VU, right? Sorry. So which is the same thing as saying 2/7 of T of V plus 1/7 of T of U plus 1/7 of T of W, which is equal to 2/7. We know what this is already. T of V was what? 2 negative 310. We know 1/7 of what? TU is 138 plus 1/7 of TW is -5, -11, 7. I'm gonna take out the 1/7 for now. I'm just gonna multiply by 2. You get 4 negative 620 plus 138 plus -5, -11, 7. So when you add this up, what do you get? You get 0. What do you get here? You get -14. And what do you get here? 35. So you get 0, -2, and 5. So what did I just find here? Third column of A. My third column of A was what? 0, -2, 5. So I did all of that to say what? This is what again? What is this A matrix? It is the nicer.
Standard method.
It is the standard matrix representation of
R3.
T, not R3, of T. It is the standard matrix representation of T. This was a lot of work. Took some time, right? I'm trying to break it down as much as I can. But like I said, if you're able to do this problem, then any other linear transformation problem, at least up until this point, that comes your way, should not be an issue. And this is only part 1 of the problem. It says find the standard matrix representation. Find the standard matrix A. We did all of this just to find it. We found it. And now it says use the standard matrix A to find T of X the image of x under T where x is 3, 2, 1. So that's this whole thing is part A. Now I want to find what is T of 3, 2, 1, right? But now we did all the hard work. All the information is embedded in this. It's embedded in it. I don't have to worry about the bases. I don't have to worry about like nothing representing one vector in terms of the other vectors. I don't have to do that anymore. I have like the genetic code. I have the code that I need that tells me exactly, precisely where this vector 3, 2, 1 will go when I apply the T transformation, which is just left multiplying by A. And then it becomes just mere computation. So I get 4. I get what? 3. 3 plus 8 is 11, minus 2 is 9. And I get 6 plus 5, which is 11. This is the image. This is the image of 3, 2, 1 under T. So look how quick part B was. Very quick. Very straightforward. Finding the standard matrix rep in this problem was harder, longer, more involved. But a good problem nonetheless. Any questions? Any comments?
So just to really quickly go over the overview. So the main idea was to get A, where A was equal to T of 1, T of 2, and T of 3.
T of
Thank you.
E3.
T of E1, E2, and E3,
Yes.
where there were a linear combination of A, B, and C.
Of V, U, and W.
And then once you found the linear combination of A1, B, A2, U, and A3, W, then
Yes.
you basically plug in that linear
Yes.
combination
Yep.
for okay.
Yep. That's exactly right. So we started with the basis. We first had to check that just in case. It was linearly independent. You can check that. It's a linearly independent set in a dimension of 3, so it's automatically a basis, which means it automatically spans R3, which is very needed. Because what's the ultimate goal? To find the standard matrix representation of T. This is the way it's defined. To find it, I must know what E1 goes, where does E2 go, and where does E3 go under this transformation. I have to figure that out. The problem is I don't know where it is. I don't know what these are. I don't know. They're question marks at the moment. So what I have to do is I have to utilize what I'm given. What I'm given is the images for these basis vectors. It's another basis. You don't always use the standard matrix, the standard basis. That's the standard one. But you have infinite number of bases for the same space. This is just one of them. What's good though about a basis is that it spans. That's the point. It spans the space, which means I can write every vector uniquely as a linear combination of those bases vectors, which I did here, and I did it here, and I did it here. To solve each of these coefficients, I must solve this system, and I can do that using my calculator. I found them. I did it for that. I did it for this one, and I did it for this one. I'm doing
Just
these-
doing inverse, right?
yeah, you have to do the inverse, right? That's exactly right. Like this is how you solve any matrix equation where A is invertible. I do that. So then, now that I know that, I can find T of E1 by rewriting E1 as a linear combination of V, U, and W. But why is this good? Well, T is linear. If T is linear, I can rearrange this expression in this way, which is very nice because I know what T of E goes, I know where T of U goes, and I know where T of W goes. They're given to me from the very beginning. They're given to me. Now I know that scalar multiplying this vector with 3/7, 2/7, and -2/7, and I do the computation, gives me precisely the vector where for the image of E1. I know it. And this is only possible based upon two fundamental things. The two fundamental things is one of them, the vectors here was a basis for R3. That's the one fundamental reason. The second fundamental reason that I'm able to do this is that T is linear. So if I have a basis and I have linearity, I have everything I need. And I do this once, twice, thrice. So I find the image of E1 based upon a linear combination of V, U, and W. I find the image of E2 based upon another linear combination of V, U, and W. And I find the image of E3 based upon the last linear combination of V, U, and W. Those images are precisely the columns for my standard matrix representation of T. So I know this is going to be my representation of what the transformation is, which means plug in any other vector that you want to choose in R3. I want to know what the image is under T. I want to know where does that vector go. Well, don't look any further. Just left multiply by the matrix A, and you'll know precisely where it goes. I still find this amazing. Like you can do this every time. All the information is here, you see? Like all of this is here. You know precisely where every vector, any vector in R3 will go under this transformation by left multiplying by A. That's kind of like, I don't know. I don't know about you guys, but I find that fascinating personally. That's why we study linear transformation so much. Any other commentary, thoughts, ideas, questions, remarks?
Yes, I do have one. So if at the top, if you do not find linear independence, then that would mean that there doesn't exist inverse of A, correct?
Right.
So then this wouldn't be possible, correct?
And you wouldn't proceed. You would be in you would be stuck. Yeah, you would be stuck, sadly. So yeah, I don't know why this is bugging out on me. Yeah, you would be stuck. And we don't like to be stuck, right? We want to not be stuck. So basis is like of having bases, like you want to have bases. You want to deal with bases. You want to deal with vectors that are linearly independent. You want to deal with vectors that are spanning sets, vectors that span the space and are linearly independent. You deal with those vectors, you have everything you need. You'll have everything you need to understand any transformation and know where everything goes. And see, it takes a while, right? It takes a while to comprehend these things, to know why they're even necessary, why are they useful. But once you get acquainted with these ideas, these definitions, these theorems, you start to like the understanding of these things starts to like, it starts to form, take shape in your mind. And then you realize, oh wow, yeah, I I definitely want to be dealing with bases now from now on. Like I see why they're useful. Because if not, I wouldn't be able to do this. I wouldn't be able to solve a system. The matrix will be not invertible, and I would just be like, just hopeless without the light, seeing the light at the end of the tunnel. But with the bases, now I can see at the end. I can see it on the other side. I can see the other side. Good. I can do one more question for you guys. Again, we'll have another session on Tuesday. Same time, 10 to 11:30. And as you can tell, to review every question, you need time. All of this is time dependent and it's time intensive because there's so much commentary to all of these problems. I can solve these problems, just show you how to do it, but it's worthwhile to go through the why, the how, so you really get what thing you're doing. So I can do one more problem, guys. And then
Professor,
yes.
I have a question. What's the joint method or joint, right?
The adjoint, yeah, I didn't
Mm.
cover that on so that was on the homework. I extended the homework to be on Monday.
I said that the review sheet.
It's on the review sheet. Where is it?
2.2.
Use determinants to determine. Okay, yeah, I have to change that.
Okay.
So you can cross this part out. I'll update it. Yeah, you can just tell me whether it's invertible. On Monday, I plan to cover adjoint and Kramer's rule, which is the last two things on determinants, and then we'll do eigenvalues, eigenvectors, and then we'll do similarity. Yeah, this took a little longer than I thought in terms of developing the understanding for determinants, because there's textbooks out there that there's a whole one chapter on determinants only. And the thing is, the book that we're using, it is one section, but that one section has multiple like subsections. So yeah, I could gloss over these things, but I don't want to. So yeah, but for the exam, I'm not asking you to know the adjoint method. So we'll see that on Monday, but it won't be on the exam.
Okay,
So
thank you.
yeah, for this section, I only ask you, is this invertible? Which means, is the determinant 0 or non-zero? So that's it. But any particular questions you want to do from any of these sections here? Anything, determinants, subspaces. If not, then it's okay.
Wait, can we do number two part C, determinants?
Number 2
Yeah, part C,
of which section?
determinants.
Yeah, the thing is, determinant has properties of determinant, invertibility of matrices, compute
Oh yeah,
determinant.
2.1 part
Okay,
C.
2.1. Okay, let me just get this. Sorry about that, guys. I don't know why this is like I'm in and out, in and out, in and out. Not sure why. I don't know. Zoom is kind of I don't know what's going on with Zoom. All right, so which one is it?
The 2.1 part C.
2.1, number 1, part C. This one?
2.1 number 2 part C.
Yeah, sorry. There's a lot of these 0.1.1.1. Okay. Okay, good. All right. Great. So yeah, this is a good problem. You have A being a 3x3 matrix. We know the determinant, we're given it, it's 4. We have B, another 3x3 matrix, and the determinant, oh, that's a typo. Should be B, Pardon me for that. I'll fix that. And I'll also upload the answer key shortly. Okay, I'll do it by today. Okay, so this should be B. I'll make that correction as well. So let me, okay. So the determinant of A, what was it? 4. And the determinant of B was -7. And I want to figure out the determinant of, what is it, 4? Yeah, 4 AB to the -1 power. I want to know what that is, knowing these two things. Several ways you can go. Several ways. So I'll ask you this. If you multiply A and B together, what kind of matrix is A and B? What's the size of AB?
-21.
The size of it.
Oh, the
Like, how
size?
many rows, how many columns do you have when you multiply A and B together? I'm not asking you for the determinants. I'm asking you for AB. Remember, A is a matrix, 3 by 3 matrix. B is a 3 by 3 matrix. So what does AB, what is AB gonna be?
3 by 3.
3 by 3. That's where I'm trying to get at. And if the product of a 3 by 3 with the 3 by 3 is also 3 by 3, then what's gonna be AB inverse? What's the inverse of a 3 by 3 matrix? What's the size of it?
3 by 3.
It's also going to be 3 by 3. It has to be. It has to be because when you multiply matrices, right? If you multiply the matrix with its inverse, you get the identity. So it must be the same size. Okay. So then this is a 3 by 3 matrix. And you're multiplying that 3 by 3 matrix by 4. What does this mean again? This 4 being multiplied? Every row is multiplied by 4. So what do we know about when you multiply a matrix by 4 to one row? The determinant is multiplied by 4. Right? But that's if I have one row, but every row is being multiplied by 4. So I'm really multiplying the determinant 4 times 4 times 4. Do you see that? So this is properties of determinants. So if you want, you can generalize this. You can say the determinant of k times a is equal to k to the n times determinant of a if a is an n by n matrix. Because if you multiply k by a, you're multiplying every row by k. And there's n rows. So when you do the determinant of that matrix, it's equivalent to saying k to the n times the determinant of a. Does that make sense? Yes or no?
Yes.
Okay. So 64 is the answer being, you're multiplying 64 by the determinant of AB inverse. But then what other properties do we know? We know that the determinant of A inverse is 1 over the determinant of the matrix A. So I can apply that property here. This is 64 multiplied by 1 over the determinant of AB. But then we also know another property. Determinant of AB is equal to the determinant of A times the determinant of B. Right? We proved that. That's the one thing we proved last time. So we're certain that this is also true. Then you get 64 times 1 over, I'm just gonna write it over, 64 over 4 times negative 7. 4 goes into 64 16 times. So the answer should be it should be 16 over negative 7. That would be my determinant for part C.
Sorry, can you please repeat, like, how did you get like 4 cube, the first part? 4 times 4 cube.
Because of this. Because of this property. Determinants. When you multiply a row by a scalar, your determinant changes by multiplying the original matrix determinant by that scalar. That's one of the properties that we saw in class. So you're dealing with a 3 by 3 matrix. AB is 3 by 3 because A is 3 by 3, B is 3 by 3. So AB is 3 by 3. Well, if AB is 3 by 3, then AB inverse is 3 by 3. So 4 is being multiplied to a 3 by 3 matrix, and every row is being multiplied by 4. So if you have 3 rows that are being multiplied by 4, then the determinant of 4 times that matrix is equivalent to 4 cubed times the determinant of that matrix.
So if it was 4 by 4, then it would be like 4 to the power 4.
It would be 256.
Thanks.
That's right. That's right. That's a property of determinants. Determinants behave like this. The computation is this. And so this question, like for example here, like these questions here exactly are just asking, do you know the properties of determinants? And there's several. So like for example, if you look at this one here, we know that this is the matrix, right? The determinant of this matrix is -5. Now, let's take a look. Yeah, let's take a look at this one. The first row, don't touch. The second row, I multiply everything by 4. So I know I must multiply the original determinant by 4. I must. And then I know another property. If I add a scalar multiple of one row to the other, you know what's really nice about that? You don't change the determinant at all. You don't. So this last row, which is adding 100A, 100B, and 100C, right? You take the first row, and then you add a scalar of 100 to the first row and add it to the third row. That does not change the determinant, which is very, very convenient for us. So if this is the determinant of A, then this is 4 times the determinant of A, which is 4 times -5, which is -20. My point here was that I multiplied the second row. I only multiplied one row by 4. But if this was a 4 as well, then I have 2 rows being multiplied by 4. So this would be 4 squared instead, and so on. But the moment I did this,
Sorry, what did you say at the last? Sorry, please, can you repeat that part?
which part?
Like you were saying, like, so you if we add another 4 in the first column,
If I multiply another row by 4,
row by 4, right? So then
this would be 4 squared
4 square. Okay. And if it is like a 3, then
and 4 cubed. And the thing is, when I write this, I'm implicitly saying I'm multiplying every row by 4, right? when I multiply a matrix by a scalar, every entry, I should say, is being multiplied by that scalar. But how does that affect the context of determinants? Well, it's every row that's being multiplied by a scalar. So that's why, how does it affect it? It multiplies 4 3 times. 4 times 4 times 4. Because of that property of determinants.
Quick question. Isn't it a, oh, sorry, I was looking at question 1. Okay. Never mind that.
All right. This is the first session, guys. I'll conclude the recording here.